because that's one of the things funny. Like someone asked me, can I count my own presentation? I'm like, no, but you're on a panel with two other students, you can count their presentation. So
Yeah. You still have to write a paper for the U1.
no, you don't. You just need to go to stuff,
I
and
see.
then you have to scan a QR code and say like, I'm at this thing.
I see. Okay. I was still writing papers until like last semester, so. Oh, well, that's okay.
And we found out like that people were continuing to write papers, and the papers were just sort of like randomly showing up. So they're still there in advisor link, but they're not being.
Yeah, that's what I was confused about last semester because I did an event. I attended the honors, the public speaking presentations, and I submitted the event. And normally they give me like a confirmation email, but this time I just did not get any.
And that was one of those things of, you do know the old link is still on the website, and I kept mentioning that over and over and over again. And I was like, I think it's still on the website, but. I said, you do realize it makes us look really bad. Things say you have a requirement and it doesn't actually exist.
Excellent, that I guess.
Because then people can question all the things that are actually like this.
I think it is being recorded.
Question. So if we want to change the committee member, does it require another form or?
If you want to change the committee member, when you do the completion form, just put the new committee member's name and email. And
Yeah, because Kishan was supposed to be here, he says he's ER. So.
I said, no, I'm sorry. The only reason I made that face is like, that's the second person who's in the ER, and like, what is going on?
No, but he had his new baby.
Mhm.
The day before,
Yeah.
I think. So I don't know what's happening, but he just messaged
Oh,
us.
no.
Yeah.
That's not good.
So we're having Paul as the.
Also, they will is here.
Okay.
Yeah.
Hello. Can you guys in the meeting actually hear me?
Yeah, I can hear you. Okay.
Okay, thank you. So we can get started. So hi everyone, I'm Monish, and I'm a senior in majoring in computer science. And today I'll be presenting my honors project.
Can you record it?
Yes, it is being
It is
recorded.
Yeah,
Yes.
great, cool.
And today's presentation is about improving team performance in multi-agent, multi-armed bandits in the presence of noisy agents. So what are multi-armed bandits? Imagine this, you walk into a casino and you are presented a bunch of slot machines, each having one arm, and you can pull an arm and you are rewarded a certain amount of money. And your strategy, your goal is to maximize the amount of money that you gain by pulling these arms, provided that you have only a fixed number of tries. And if the money returned by these slot machines is constant, then your strategy may be just go through all of the slot machines, pull them once, and then pick the one that gives you the most amount of reward, and keep pulling that one until the end, so that you can maximize your reward. But say that this reward is hidden behind a distribution, so you're not always given the exact true amount of money, but it is sampled from a distribution that is hidden from the player. Now, if you play the arm, all of the arms once, and if you get a lower amount of money from a slot machine, it does not necessarily guarantee that that is the true reward that you will receive in the future. So you have to kind of balance this exploitation versus exploration process, which the multi-armed bandits framework helps us do. So formally, it is a bandit has K arms, and behind each arm is a true mean called mu star, which is hidden from the agent. And each time you pull an arm, that reward is sampled from a normal distribution with a true mean of mu and the variance of sigma. And the goal is to find the optimal arm through this exploration process. So you might ask, why bandits? So in the real world, there are several scenarios where this bandit framework helps us solve some problems. So one really good example is recommendation systems. So take a service like Netflix, for example. The Netflix is trying to figure out what your interested genres are. So it has to recommend you certain movies, and then if you click on some movies or click away from it, it has to adapt its strategy so that it can recommend you movies that you would actually like. So this is the kind of exploration where you try to recommend new genres that the user may or may not like, and you exploit whether you know that the user likes this kind of genre and you recommend in those movies. And this kind of process also applies in ad placement, where you select certain kinds of ads or personalized ads on websites. It applies to dynamic pricing, and it also applies to parallel computing, where you have a distributed system and you want to load balance the process in that system. It also enables for faster testing of evaluating different team structures in this kind of exploitation scenario, and we'll get to that in a minute. So what are multi-agent, multi-armed bandits? So far, we've talked about only single-agent, multi-armed bandits. So we can introduce multiple agents in this scenario to be able to solve the problem quicker and more efficiently. And we can represent this team structure as a graph structure or a communication network. And the goal is to share information among these agents so that you can converge to a consensus faster and maximize your overall team reward in the long run. So there are a couple of single agent strategies that you can use. One really naive strategy is called epsilon greedy, where you select the best arm that you think is the best for a certain percentage of the time, and you select and then you try to select randomly. So that is the exploration portion the rest of the time. So more formally, you are taking the arm with the maximum estimated value that you think with 1 minus epsilon probability, and then you pick a random action the rest of it. So that is a really naive strategy, and it does not give preference to, or it does not pick its random actions cleverly. So there's another strategy called UCB, upper confidence bound, in which this exploration portion gives some more preference to arms that have not been selected as many times. So you exploit a certain amount of the time, and then you explore the rest of the time. And in this exploration portion, you try to explore arms that have not been explored that much, because that would give you a better estimated value of those arms rather than just picking the arms that you already have a good idea of. So we can see that in this formula is almost similar to this argmax of QA, where QA is the estimated value of the arms, but we introduce a new portion, which is important for this exploration portion. And we can see that this ratio grows larger as the number of times you select an arm is lower than the other arm. So N of A is the number of times an arm has been selected, and if it's lower, as time passes, this ratio grows larger, so you give preference to these arms that have not been explored as much. And now moving on to multi-agent strategies, there is an algorithm called co-op UCB2, which is also based on the single-agent UCB algorithm that we just discussed. This uses a consensus-based strategy for cooperative estimation of means and the rewards of the arms. And being consensus-based means that each agent can experiment with these arms and then communicate with each other. And we have to make sure that this communication is efficient so that we can converge to the best arm faster. And this is the consensus update formula, where you have to update the estimated value of each arm in every step as the agents pick each arm. And this one also is similar to the previous equation in the sense that you have the exploitation portion where you try to estimate the value of each arm, and then you have this exploration portion where you try to cleverly assign like a certain weight to the arms that have been explored more or less. So now that we have these strategies in place, we have to measure this team performance in some way so that we can evaluate different algorithms and the strategies. So one really popular metric that we use to measure team performance is called regret, which is the difference between the expected reward by picking the best arm always, that is, assuming you know what the best arm is, and the difference between that expected value versus the actual reward that you receive by playing the bandits. But this might not always be the best metric to look at because the reward is sampled from a random distribution. And we want to eliminate this randomness as much as possible when we're trying to evaluate team structures. So we use something called a pseudo regret, which is the difference between the true mean of the best arm and the true mean of the selected arm over the course of this the experiment of running the bandit. So we can plot this cumulative regret over time, and we can say that the lower the regret, then the better the team performance, because obviously if you're picking the best arm most of the time, then the difference between the reward given by the best arm versus the reward given by the arm that you pick, which will happen to be the best arm, will be lower. So this co-op UCB2 algorithm works based on a consensus, as we discussed, and it relies on this principle of social learning, which also known as distributed averaging. So this is a core concept. It's formalized by this degree learning process, where you have a vector of opinions or the initial node values that can be iteratively updated by some transition matrix. So it is given by this formula xt equals p xt minus 1, where xt is the initial node values. So to give a bit more explanation on that, imagine a team structure that is working together to solve this bandit problem. And each node starts with an initial guess or an estimate or an opinion about this environment. And they have to communicate in this graph structure. And P is a matrix that represents this graph structure. And you iteratively update this opinions in order to reach this consensus over time. And in co-op UCB2, we have a similar step. It's given by st equals p times st minus 1 plus rt. In this one, we are also including the reward that we receive from the environment, because that is an important step to update the estimated reward that we are receiving from each arm. So st is the estimated cumulative reward vector at a given time t for arm I, and rt is the reward vector given by arm I at time t. So we add this reward to the existing node values, and we multiply that by this transition matrix or the weight matrix that is defined by the team structure, and then we update our own node values. So as we discussed, the P is also known as the run matrix. It is a matrix that shows how the information is shared throughout the network. And there are certain constraints on this matrix. Mainly, it has to be doubly stochastic, meaning the rows and the columns add up to 1. And where each element in this matrix represents the weight of each edge or the node of how the information is shared. So it basically dictates how the information propagates throughout the network after each time step, after pulling an arm. And it also has to be positive, but this can change based on some optimization algorithms that we use. And this is the consensus step that is used in co-op UCB2, where you have two vectors, n hat and s hat, where n hat is the estimated number of times an arm has been pulled, and s hat is the estimated reward, cumulative reward given by arm. And it is updated by two vectors, which is C and R. And C is the number of times an arm has been played in the current time step, and R is a reward vector in that particular time step. And we update S and through every time step based on the same iterative linear iteration process. And so since P directly dictates how this information is propagated throughout this network, it's important that we can optimize this matrix in order to achieve the consensus faster. And because with an optimal matrix, we can hope to minimize this cumulative regret over time and improve the team performance overall. And so the goal here is to find an optimal P matrix. And the method is to apply existing optimization methods on graph-based communication networks to show that the team performance can be improved in a multi-agent, multi-arm bandit context, in comparison to some existing heuristic methods, which we'll talk about. So there are some existing heuristics that we can use to set these edge weights in a given communication network. And we'll talk about 4 of those heuristics. One is called constant edge weights, which uses something called a Laplacian matrix to set its P matrix It is basically derived by subtracting, or is basically derived by I minus alpha times Laplacian. But the Laplacian, you can think of it as an adjacency matrix, but overlapped by the degree matrix. And it is another form of representing a communication network. And alpha is some constant that you picked that you can use to manually tweak your matrix, which is why it gets its name constant edge weights. And there are some strategies to pick alpha smartly, but we'll get into that later. And another strategy is maximum degree weights, which uses the same principle, but instead of alpha being manually tuned, it uses 1 divided by Dmax, where Dmax is the maximum degree of any node in the graph. And there's another strategy called stepwise max degree, which is used by the authors of CoopTCP2, which also uses the same strategy, but again, slightly tweaked, where alpha is given by kappa divided by the max degree, where kappa is now another constant that we have to manually tweak. And the last heuristic is the local degree weights, which is also known as the Metropolis Hastings weights, where we assign the weights based on the maximum degree of the neighboring nodes of any given node in the communication network. So now that we've discussed the heuristics, we can discuss the main algorithm that we're hoping to use to optimize the multi-armed bandit or the team structure in multi-armed bandits. It's called least mean square consensus, also known as LMSC. It is a distributed consensus algorithm that considers the error in the average values over time, and which is introduced by the noise in the communication network in order to optimize the team structure. So this is formally known as mean square deviation, and you might have heard this when doing linear regression, where you're trying to plot a best fit line for any given data, and you're trying to calculate the error between the data that is existing and the best fit plot line. So this is a similar idea, and you're trying to minimize this mean square deviation. So LMSC, how it works is it works by formulating this problem into a convex optimization problem so that we can efficiently compute the solution. And we'll talk about how this works. So as we discussed before, there's this notion of distributed linear iterations where you have a set of initial node values that are constantly updated by this P matrix, which is a transition matrix. And to achieve average consensus, you have to satisfy certain conditions. And this condition is that over time, as t reaches infinity, your node values must converge to some average value, which is the consensus. So that it can be given by this notation, which is 1 divided by n times the rank 1 matrix. And this is not to be confused with just an integer 1. It is a vector of 1 multiplied with its transpose, which is a matrix of all ones. And that multiplied by the initial node values gives us basically the average values in all the rows and columns. And this matrix also needs to satisfy some other conditions, which is P has to be symmetric, equal to its transpose. All the rows have to add up to 1, and P has to be an element of this set S, where S is a set of all possible team structures, or all possible relational weight matrices for a given team structure. So now that we saw that linear iteration process without noise, with noise, it would just have an additive term called VT, which is a vector of noise variables on each node. And when we average that out, it turns out to be AT plus 1 equals AT plus, again, the average matrix that involves these new this new vector of noise values. And since this noise is random, it can be proven that XT is still a stochastic process without the noise term. So XT is still being updated just as though the noise term is not there, but now there's more deviation in the average values that can also be modeled by another sequence of random variables. So because we have this noise, the nodal values now don't converge meaningfully. Without the noise variables, they will eventually converge to the average consensus, but we have to consider that there's noise now. And this can be done by modeling this mean square deviation, as we discussed before. This is the deviation of the node values from their averages, and that can be represented by delta t, which is the expected value of the deviation from the node values and the average value, which is the consensus that you're trying to achieve. And you want to this delta has been proven to achieve a steady state as t reaches infinity. So we know that as we go through this banded or this learning process as t reaches infinity, the limit of this steady state converges to the limit of this delta converges to some steady state value. And our goal is to minimize this steady state value. So now we can formulate the LMSE problem where you're trying to minimize the steady state as which is written as a function of p, because we are trying to minimize the steady state deviation where we use p matrix as a team representation. And the conditions that we impose are that, again, p has to be a symmetric matrix, the rows have to add up to 1, and p is an element of a set of all possible team structures. And we have another condition, which is p, the norm of p minus j is less than 1. This formula gives us the spectral radius of a given matrix, which can be thought of as, so j is the average matrix of a given team structure, but without the initial node values. So you want to minimize this, or you want to keep this spectral radius less than 1. It can also be formulated using the eigenvalues, which we'll talk about later. And LMSE problem uses the gradient and the Hessian, which are the first order partial derivatives and the second order partial derivatives of the delta steady state deviation to solve this problem. And so now we need to form the LMSE problem has to reformulate these conditions in order to be able to compute this based on the information that we have. So P can be rewritten using the edge weights and the teams and the structure of the team. So what do I mean by that? It can be rewritten using W, which is the edge weights in the team structure, and A, which is an edge list matrix or the incidence matrix that we can derive basically by just the team structure that we set in the beginning of the experiment. And this is, and P can be said to be I minus the sum of these edge weights times the incidence matrix for each edge in the given network. And the goal is now can be rewritten as P being this new formula where you want to minimize the steady state mean square deviation of this given this P matrix, and that is subject to the condition that the spectral radius has to be less than 1. So as I just mentioned, we can model this steady state mean square deviation to be as a function of P, because P is directly impacting how this noise is propagated throughout the network. So, and that can be derived to be this formula, which depends on the eigenvalues of this P matrix, which is represented by lambda. So now now that we have modeled all of these or reformulated the problem with the variables that we have, we can minimize the function that that is given by this mean square steady state deviation of the edge weights and the incidence matrix. And this is also shown to be a convex optimization problem. And if you're unfamiliar with the convex optimization problem, it is basically a function which has only one minima or minimum. And so basically you start from a point, from some initial state in the function, and you try to work your way to the global minimum so that you're optimizing. You're finding the point where the result of the function is the least. So we can use several methods to achieve this. One really popular method is called gradient descent. There are some other methods called quasi-Newton methods, etc. We chose this very conveniently named Broyden-Fletcher-Goldfarb-Shannon algorithm, also known as BFTS, just because it was ready to use with the SciPy library that we used to compute this or solve this problem. And the initial estimate for this optimization problem was picked using the Metropolis-Hastings method, which was also shown to be effective to find the minima of this function by the authors of LMSE. And so now we get to the experimental setup. We used 10 armed bandits, meaning there's a bandit with 10 arms with 10 different true means. And we run this experiment for 500 time steps for 1,000 runs. And we do 1,000 runs because we can average out these reward or the regret values, and we can get a smoother curve over time. And we have one faulty agent in every network. So here's the results for some 5 agent networks that we will discuss. So we have 3 networks here. One is where all the nodes are connected to all other nodes. One is where they're connected as a ring, and one is where they're just connected as a house shape. And we can see that might not be clear based on the colors and the overlapping, but LMSC does do slightly better than other weight setting methods. So especially when compared to the stepwise max degree, which was used by the authors of co-op PCB2. But you might notice that it is actually not doing better than other heuristics that we discussed, namely constant edge, max degree, and local degree, which is also known as metropolis heuristics. So, and this same behavior can also be seen in larger networks. So we used an 8-agent network, where it is again the same behavior, where LMSC does better than one heuristic, which is a stepwise max degree, but again, does similar to other heuristics in our list. And again, if we go up to a 21-agent network, where the network has been distributed in such a way that we have 2 colonies that are connected by one bridge, so that we can see how the information propagates through these different colonies, basically. And since we have 21 agents, we cannot, or it would be trivial to use a 10 armed bandit, because you can just go through them in the initial pass and maybe accidentally find the best arm. So we bumped it up to a 25 armed bandit to make it harder for this 21 agent network. And again, it's the same result where LMSC, it does do better than some heuristics, and now even better than constant edge, but it's still overlapping with this maximum degree and the local degree heuristics. And we also have some unexpected results where we have a 5-agent network with in a star configuration where there's a central node that is connected to all of its child nodes. So it's basically like a tree, where LMSC straight up performs worse than every other heuristic in our list. And we haven't been able to explain why exactly this does in comparison to the other heuristics, which leads us to the discussion of the performance of LMSC versus the other heuristics. So we show that it is better than some heuristics in our list in some networks. As we can see, it worked in all the ring network and the house network and the 8-agent network as well. And the most significant difference being between the method used by the authors of co-op PCB2, the stepwise max degree, and LMSC. But when we compare it to other heuristics such as local degree, constant edge, it falls apart. So some of our hypotheses or possible explanations are the added noise in the system was not enough or was not appropriate in this multi-agent, multi-armed bandit context. And it is not enough to show that that this improvement is actually significant in this specific case. Another explanation is that the specific multi-agent, multi-armed bandit algorithm that we chose, called co-op PCB2, maybe it is not an optimal test bed for our optimization that is promised by LMSC, because we are only testing with one multi-agent mob context mob algorithm, but there are several algorithms that we can use. For example, there are other types of algorithms called gossip algorithms, which work slightly differently, but are still consensus-based. So this is something that we can experiment with in our future work, which is just the next slide, where we can experiment with different levels and different kinds of noise. And what do I mean by different kinds of noise? So a noisy agent can be an agent that, say, it lacks the ability to see the information properly. So imagine a search and rescue mission, for example, where the agent has faulty sensors. So it reads wrong information from the environment, and it gets wrong information for itself, and it propagates this wrong information. But you can have a different kind of noise where it is a faulty agent or a malicious agent, where it reads the correct reward from the environment, but it propagates a different kind of information. We can also, as we discussed, we can also experiment with other multi-agent, multi-armed bandit algorithms. For example, a variety of the gossip algorithms that already exist. We could also use harder bandits. So instead of just having 10 armed bandits, we can have 50 armed bandits or 100 armed bandits with higher variances, so that we can push the limits of these consensus algorithms. And we can also experiment with more than one faulty agent, which also falls under the category of different kinds of noise or different levels of noise. so that we can introduce more sources of this faulty information into the network. And so to recap again, we used LMSE to show that we can optimize and improve the team performance compared to other existing heuristics in a multi-agent network. And our results show that the team performance can be improved in some networks in comparison to some heuristics in terms of regret. But we have to acknowledge that there's still more research that needs to be done to investigate the trends that we are seeing in comparison to other heuristics. And that brings us to the end of the presentation. And thank you. And I'm open to any questions.
From here or you?
Let's open the chat just in case.
Oh, they.
I can ask a quick question to start us off. So you touched on this a little bit towards the end of your talk, but what sort of applications does your work here work better with? What would be the next steps towards applications? Like you talked about search and rescue. I know we have a project where we're focused on that. But basically, if I was building a robot, when is this good to put on my robot? Or when should I investigate if this is good to put on my robot? Or when should I go some different direction?
Okay. So I imagine this to be useful where you have robots of different skill levels or with sensors that are highly likely to fail. Maybe it's in a harmful environment, and you need to be able to deal with any kind of noise that are originating from these robots that have a high chance of failure. Or there can be some sort of failure in the communication itself. So you might not always be able to relay this proper information in some tough environments. And you would want to kind of optimize this network even in the presence of such noise. I hope that answers the question.
In the consensus, right?
In the consensus, yes.
Yeah, that's what I was looking for. Thanks. Good talk, by the way.
Thank you. Any other questions?
So just to add that Manish is in one of our projects. So this is his main stuff that he's working on, and he got to this point yesterday. So it's an ongoing thing, and he's writing a paper. So as soon as we can clear up some of the results, the paper is ready to go. Yeah, any other questions from the chat? No.
Actually, I got one.
Sure.
Okay, so you showed that the study graph, I believe it was, the one that has a single node in the middle of the tree.
Right.
Do you have any idea why that performs so much worse?
So that's something I've been trying to explain or mathematically prove, but no. For now.
Which agent is faulty? Is it the middle?
So it is actually the middle one, but I have also experimented with the leaf nodes, and it still results in the same performance. Just that the scale is now downshifted because the central agent is not faulty when you have a faulty leaf node, but it's still the same result where LMS still looks worse than other heuristics.
Even if you had a bunch of other like outside nodes, not just like 4.
That actually we still haven't tested. So maybe it might just be that there is less information coming in because we have only 4 agents that are connected to the central node. So that would actually be interesting to try with like 10 other agents connected to the central node.
Yeah, for middle makes sense because then you're receiving for the other one, the only source of information is that middle to share, right?
Yeah.
So it's like a 50-50. You send good information, receive bad information. The average is still not good.
Yeah.
For the sides, I have to look at that. And then it would be great if you can, not here, but later, identify in your figures which one is the faulty.
Right. I can
So
highlight the
people can
ones that
think
are-
about.
Right.
And in we go to the large network. So it will not be very significant effect because one agent being faulty will not affect Unless you pick the middle one.
I actually specifically picked the middle one or one of these bridge nodes to be the faulty one so that I can see some effect. And it make a difference when I pick this versus say one of these little ones.
No. If it's on the side, it's not very important. They're just
Exactly.
the vastness of the information which covers the noise that you will not do.
Right.
All right, any other questions? Nothing. Everyone's sleeping. All right.
Thank you, everyone,
Thank
and
you for the time.
I hope to see you soon.